All right. So now what we're going to do is we're going to create a device, and this is going to get us our capacitor. So the first thing I want to talk about is charge density. And if you watch the videos for looking at the Gauss's law, when we talk about charge density, we're going to use this sigma, and that's my charge per unit area. Because we're going to be dealing with areas, we're going to be dealing with a variety of things. So this is one thing that we're working with. So if I had a positive and a negative plate, and now I'm going to talk about a potential across the plate, we can look at my electric field in that is going to be my difference between my B minus my A divided by my distance. And that gets us back to our change in potential divided by distance. And remember, my potential is my potential energy divided by Q. This is now a device. And this device is called a capacitor. And we will have it look like this in our circuits. So that represents a capacitor. Some of you may have multimeters, and this it might be this symbol that you see on a capacitor. So these two things represent capacitance. And this thing can store charge. The other thing that we're going to see is a battery is a special case. And this is the symbol for a battery. And this is the positive side, and that's the negative side. All right. So now if we do that as a device, let's look at our E. D is equal to my change in potential. This is my KQ over R squared times my D is going to equal my potential. And if I rearrange these things, KD over R squared, charge is equal to potential. This part of the equation is dependent on the configuration. That's a constant. My distance and my radius is what's there. And this gives us our definition of capacitance. Capacitance is a C, and it's coulombs divided by volts. And this is going to be in a unit called a farad. And that gives us our units of capacitance. So it's the ability to store charge. So capacitors are going to store charge. So we can play with these, and what we end up doing is we end up talking about parallel plate capacitors. Plate capacitor just looks just like this. I have two conducting materials. I'm going to be able to apply a voltage across. And that's what's going to build my capacitor. And it turns out that my electric field goes back to my charge density, right? Remember, we've seen this with my Gauss's law. And now if I rewrite this, this is my charge per unit area times this. And this is for parallel plates. And we can actually make a device that has specific capacitance that we want. And what we end up doing is by rearranging, we get our permittivity is free space, our area divided by the distance is going to give me my charge over my change in potential, which is defined as my capacitance. Okay. So what happens is my area increases, the capacitance increases. As my space decreases, my capacitance increases. Now I can put a material in here. It can be different than air. I could put a piece of plastic, I could put a piece of paper, I could put something that's non-conductive. Then I can look at my change in potential is going to equal the one that's in air, and then I use this little kappa, and this is what we call the dielectric constant. So I can modify my device based on my dielectric constant. And then my new capacitance is the dielectric constant times where it is with an open space. And K is equal to 1 for air. And the more general form for this would be to add that K to it. So let's get to looking at putting these things together. You can put capacitors and then I have a voltage. This is parallel. Or I can put capacitors in a system that looks like this. This is in series. And what happens here is I'm going to store charge, and the total charge is equal to the charge on this one and this one. And remember, Q is going to equal C times the change in voltage. So if I'm going to look at my total, this becomes C change in voltage. And this is C1, 2. But look at my configuration here, and my change in voltage is going to be this configuration. So now I get C times V. This is going to be the equivalent capacitance is equal to C1 V 2 V. And so my equivalent capacitance is just going to equal C1 plus C2. Now, when I do this one, my change in voltage across these two have to be added up. And we're going to do my voltage is going to be Q1 over C1 plus Q2 over C2. And I get Q total over C equivalent. But this Q and this Q and this Q are all the same. So now I get C equivalent is equal to 1 over C1 plus 1 over C2. Now, when you're working your problems and looking at equivalent capacitance, you've got to make sure you're keeping track of those. And I will put some example problems into Blackboard. We also want to look at the energy stored. And the energy stored is going to equal 1/2 Q delta V. It's also equal to 1/2 C delta V squared, or it's equal to the amount of charge divided by 2C. And all of that is just rearranging our energy equation. So just because brains are full and I don't know how much longer my Zoom will be stable, I'm going to put this particular one up, because what we want to do is find the equivalent capacitance for the following. These are in parallel. These are in parallel. These are in parallel. So I can calculate those out just by adding them up. And then I can redraw my system so that now I've got that one is 8, that one's 8, that one's 11. And now I will do this part of the calculation. Get that, but I have to flip it in order to get my equivalent capacitance. And again, I will add a variety of problems in there. Here's just another problem looking at what we've been talking about today so that you guys can have this in your notes as well. This is looking at, we want to find the electric field. We want to find the force on the electron. We want to find the work that's being done. We're given the separation of the plates. We're given our change in voltage. So we can actually just work through the various calculations. And let me move that up so you guys can get the whole answer. And I am recording as long as the recording is working for my Zoom. And that, folks, gets us through the next chapter.